Greetings. Here we have an eye-catching question. So see here we have interconnection of ideal sources. We have four ideal sources and we have couple of current sources and again couple of voltage sources we have. It is interesting that there are no passive components in this beautiful network. Now it is known that this 60 volt source, the 60 volt source is absorbing power. Yeah. So question paper setter, he gave us an hint or he gave us a way to find an answer, right? So it is known that 60 volt source is absorbing power. Now which of the following can be the value of this current source I? Yeah, so you have four options, 10, 13, 15, 18. Yeah, what would be the correct answer for this? So anyways, we will come to some conclusion later part. See, in this case, let's go for solution. Now what data we have here? So 60 volt source is absorbing power. Now you see, let us take some element. Yeah, let us take some element. Okay, this is some element. Now say polarity is something mentioned like this, plus minus. Now say this element, say this is a voltage source. Element could be voltage source or current source or resistor, capacitor, inductor. You can treat anything as an element in literature. So let's take a voltage source like this. Let's assume that some current is just going all the way. Okay, say it is just going clockwise direction. Now current is entering at negative terminal and is going to exit at this positive terminal. So in this case, now what happens? So this is current, right? So therefore in this case, this element, this element, now it is delivering power. Yeah, so this element is delivering what amount of power? V multiplied by I. Now that power delivery is negative. So in this case, power delivered is negative. Whenever we see delivery or supply, you have to treat that quantity as negative. That quantity here is voltage multiplied by current, that is power, is negative in this case. So when you see like this, you have to understand you have delivery or supply. Now what happens in reverse case? That is, say for example, this is case 1. Okay, let's take case 2. Let's take case 2 like this. Okay, so let me take some element. All right, say this is some element and you have this element is again say voltage source. Now let me take my another color. Now see, if there is current like this, yeah, if current is coming all the way and it is taking anti-clockwise journey, now current is entering where? Current is entering at positive terminal, so it will exit at a negative terminal. Now this element is absorbing power. Why? This element is absorbing power. How? Given like this, the 60 volt source is absorbing power. That means current has to come like this. All right, so in the initial run we have to decide this. Okay, so see, gate problems are always like this. You must be able to utilize the given data. So the given data is this. Apply your beautiful concepts and try to find some path like this. So therefore we found a path for current like this. Is current a scalar or a vector? Yeah, current is perfectly a scalar quantity, not a vector quantity. Charge is scalar, current is scalar, current density is a vector quantity. Yeah, anytime a surface could be vector, volume could be scalar. So anyways, we have lectures on electromagnetics. There we will unlock all these things. Now come to the story back. See, Now here, so we have decided direction of current like this. Yeah, current is entering at this positive terminal here, so that means we could say now this 60 volt is absorbing power. All right, so here we have KCL. So first of all, at this node, KCL must, Kirchhoff's current law must hold. What is Kirchhoff's current law here? Conservation of charge at a node. That means at this node, charge should never accumulate. Okay, so that means to hold KCL or to make a KCL to get satisfied, you have to see to that charge is not accumulating. Okay, so therefore at that node, at this node, algebraic sum of currents, say algebraic sum of currents must be 0. If it is the case at this node, so we could say KCL holds here. All right, so now now let's try to satisfy this KCL. Let me take one more. Let me take this one more page. Let me redraw it here. So here you have 60 volt source DC. So and here you have one more source, say polarity is mentioned like this, and here you have one more source. All right, so now see, all ideal sources are communicating at one place. Beautiful, right? So now here you have again one more ideal current source. All ideal sources are friends. They formed a community, that is ideal community. Okay, so given like this, and we have marked a node here. So at this node, KCL has to satisfy. So now see, if you observe carefully, here we have source current 12 amperes. Now this source current would be branch current, now 12 amperes, same 12 amperes we could see here, and this 12 ampere would flow through this 20 volt source. See, it's entering at negative, exiting at positive. So therefore he is what? Rising voltage. Okay, he is not, this is not drop, he is rising voltage. So again same 12 amperes will come here. So all the way you have 12 amperes here. Now 12 amperes is here, and this direction shows that I is exiting, I is leaving from this node. Okay, now let's take entering, let's take entry as negative. Okay, let's write it here. Let me put here, let me take like this, entry we take it as negative quantity or negative value, and exiting or leaving, exit or leaving, we take it as positive value. So positive current, yeah, and this is negative current at the node. So now to satisfy this KCL at a node, now what we do, so at this node, so 12 is entering, right? So 12 ampere is entering, so negative 12, and this I amperes is leaving from this node, so leaving we are taking as positive, so take positive. Now at this node, algebraic sum of currents means currents, the plural form of currents means that could be, you have a combination of some entry currents and combination of exiting currents. So at the node, those combinations put together must be equal to 0. Okay, so negative 12 is entering and I is exiting like this. So therefore to balance this, now what you do, to balance this, somehow I must make minus 12 to positive 12 and this positive I to negative I. If I do so, happily we can make 0 in the right hand side. Okay, so therefore I must get positive 12 minus I. So I must get positive, see, positive 12 minus I. So positive current, yeah, in this case is like this. So that must, I mean this current must leave this node. Okay, so this current must leave this node. So therefore you have 12 minus I. Okay, so 12 minus I amperes is flowing through this 60 volt source. Now you observe again. Now this 12 minus I ampere is entering at positive, and it's given that 60 volt source is absorbing power. So therefore what we must have, let me write here, 60 volt source is 60 volt voltage source is absorbing power. It is absorbing power, and this power quantity must be a positive value because it is absorbing current entering at positive terminal. Okay, so if this is the case, now what can we conclude from this? We can conclude this beauty. So you see, what we can conclude is power means in this case what? So I have 60 volt here. So 60 voltage multiplied by current is power. So 60 multiplied by 12 minus I. Okay, so 60 multiplied by 12 minus I, this must be what now? This must be a positive value. Okay, so when it is possible, when can we say 60 into 12 minus I is positive? When I is less than 12 amperes. Yes or not? If I plug in I anything less than 12 amperes, then 60 times this quantity becomes positive. All right, so now without solving further also we can find it out, the correct option here, right? So see, I less than 12 amperes. Now in the given, see from the options here you have 10, 13, 15, 18. The only option which is less than 12 is 10 amperes. Yeah, and fortunately don't have any option none here. If there is none, we must be able to satisfy, we must try to find what is option A again. So there is none, so definitely we can take I is equal to 10 amperes in this case. But of course we can satisfy this. Yeah, see, happily we can satisfy this. Coming back to this latest page. So now you see, so this is positive, right? Anyways, again here we have a node. So at this node, if we take I is equal to 10 amperes, so one of the options we have 10. So let me take I is equal to 10. So what do you have now? So we have 2 amperes now. So 2 ampere is entering here, and now we understood I must be 10 amperes. So here we have 10, and again we have 10 amperes here. Okay, so entry this is entering at this node, right? So I'll take entry as negative 10. Okay, I'll take entry as negative 10. This fellow is also entering, right? So that is 2 amperes is again entering. So again entering at the node, at this node again I take negative 2. Now from this node, see, from this node, say this current is now exiting. So this source current becomes here branch current. So positive 12 amperes here we have. That means as this current is leaving or exiting, so I can put positive 12 here. So at this node, algebraic sum of currents must be 0, and of course it is 0. Yes or not? So therefore it got satisfied everywhere at this node and here as well. Okay, so it is very, very important. If you have an element, if current is entering at negative terminal, now this element is going to deliver something. Okay, now if you have an element and if current is entering at positive terminal, now this element is going to absorb something. Something is what here? Something could be energy or power. Yeah, see, in literature of circuit theory, you don't have anything beyond voltage, current, energy and power. Yeah, so you can play with these 4 quantities in circuit theory. It's all about mere 4 quantities. That's it, V and I. If you go to field theory, slowly we forget about V and I. Then we have to accept sometimes trouble, right? We have to accept E and H. So grandfather, electric